So yes, so far we've been seeing lots of feedback, but not the typical feedback that I've been studying, which is basically the effect of these supernovae and massive stars, but on much larger scale, well beyond the immediate surrounding of these stars. And I need to thank for some of the slide cat that is going to talk next, and also Chris, who may be watching right now. Because I've been using some of the slides, and I do appreciate that. So I've been tasked to talk about the Magellanic Clouds, but what I'm going really to talk is the LMC mostly. And the reason is, well, the SMC is actually very hard to actually study, because one of the way that we're actually studying these flows is using spectroscopy, and we are trying to see whether which velocity component is associated with what gas. And because the SMC in velocity is much closer to the Milky Way, it's actually much difficult to actually see large-scale flow from the SMC, or at least to differentiate them from confusion. So having said that, some motivation. So yesterday we've been, and today also this morning, we saw that, you know, this the LMC and the SMC have these huge super bubbles, and so you have this the association. And one of the things that we know eventually what should happen is that some of these super bubbles will expand and actually blow some gas well beyond actually their surrounding into the above the disk, above and below the disk of a galaxy. And so these models are not new. But basically, here is one of its representations, and one of the ways that we can trace this gas is to look for this tracer of relatively hot gas, where hot in my talk will be a few times 10 to 5 Kelvin. So it's not the million-degree gas traced by X-ray, because, well, we don't have a resolution yet in X-rays to really do this job as we do in the UV spectroscopy. But we have great UV spectroscopy tracer, the Oxygen 6, Carbon 4, as I'm going to mention. And so the game here is to see if we see any influence of these different super bubbles well beyond the disk of a galaxy itself, of the LMC here in this case. And the motivation for this type of work is actually well beyond just to study the Magellanic Cloud, but it's a cosmological motivation, because what's happening in the surrounding of the galaxies, this extended halos, or also as we know it now, the circumgalactic medium of galaxies, is really critical to understand, because it's basically it's the place where the evolution of galaxy is driven. You have these massive inflows and outflows that compete around galaxies, and the way that, and I think I will not say anything shocking in this room, is that the way that feedback is treated in this large-scale simulation is very crude at best, because basically they're trying to simulate both what's happening on very large scale and what's happening in the galaxy, and typically they don't actually have a spatial resolution to resolve a star. So, and they try to model basically the supernovae, or the effect of the supernovae on extremely large scale. So the way that is done, they tune this parameter to fit some the galaxy observations, but really what we'd like to do is really to see the physics that is actually in this simulation is actually correct or not. And we can actually do that by studying the gas phase physics in around galaxies. And the LMC is actually the only place where we can study not just one line of sight per galaxy, but hundreds of line of sight thanks to different observatory, and in particular the FUSE observatory that Bill Blair already mentioned yesterday, but also probably future COS observations, TIS observation, and so on. And so the LMC is great. It's a disk galaxy, so dwarf disk galaxy. Its metallicity is lower than the Milky Way, so it could be serve as a reference for higher redshift studies. Again, we can do very high spatial resolution, and so we can actually try to see if there is any relation with the gas that we think well beyond the discovered galaxy with actually what's happening in the LMC. And yes, it's the only galaxy where we can actually resolve the individual stars. But it's not all so good, because the proximity is also an issue, because you have a lot of contamination from other things, and in particular our own Milky Way. So I'm going to show you in the next slide. When you look at the UV spectrum, you have different velocity components, and to differentiate the origin of this component is actually a pretty tricky business. So it can be a tricky business. And also, when we're interested to see if there is gas on the LMC, well, we know that there is this beautiful Magellanic stream, and it's basically everywhere. It's really very complicated to differentiate if this is a gas that has been put out via interaction between the galaxy, which actually outflows from stellar feedback in the LMC. The LMC, well, is nearly face on. That's great, because we can study different regions of the LMC, but it's also an issue because we don't have any information about where the gas is along the line of sight here. So it's all projected, and so we need somehow to, we need to really study to show that there is actually large scale, as I'm going to show, large scale flows in the LMC. And if you want to compare the results from the LMC to higher redshift galaxies, here when I'm talking higher redshift, it's really low redshift galaxies, but redshift less than 1. It's actually not so easy, because it's actually not a very much star-forming galaxy per the definition of higher redshift. The LMC is currently forming about 0.2 solar mass per year. And the overall star formation rate is and typically it's much higher when they study galaxy at higher redshift. So the comparison is just not straightforward. But so the question of this talk, what I'm going to try to address, so is there some of this large scale flow associated with the LMC, or only the LMC, not the interaction between the LMC and SMC? Is there a global component, a halo, around the LMC? And is there any connection between what we're seeing maybe in this halo and what's happening in the disk of the LMC? So the way that we study this, we use the stars in the LMC, so these hot stars that people study with hot star. Here I'm studying actually the gas that is between us and these hot stars. And here is a typical spectrum. It's a very busy plot, but basically here you have a normalized flux, and here you have the velocity, here in the local standard of rest. And basically what you have here is different ions. So here you have carbon-4, silicon-4, oxygen-6, silicon-2, sulfur-2, also the plot is complicated. You have oxygen-1, and you have here at the bottom the iron-3. And why do I show this? It's just to show you the rich information that we have from UV data. We can do actually gas phase just by looking at this. So here at 0 kilometers per second, you have a Milky Way. Here around between 200, 300 kilometers per second, you have the LMC component. And in between, you have all this stuff that we call intermediate and high velocity cloud that I will not talk today about. If you have questions at the end of my talk, please ask. But just by looking at the spectra, the gas goes from neutral phase to intermediate ionized phase to highly ionized phase. And you can see also when you look at the profile, the oxygen-6 here, it seems to be very unique in the sense that it's just a very broad oxygen-6 absorption, and it's very different from all the other ions that you're seeing. In this paper, I actually try to deconvolve. So in the carbon-4 and silicon-4, they can actually be photoionized by the star itself, the region around the stars. But if you do profile fitting, you can actually find that there is actually a broad component that goes with the oxygen-6. But it's actually not so easy. So that's all the information that you get from this type of spectra. So how do we, and in particular, I get this highly ionized gas, which is a tracer of this hot gas, so this component that's actually may directly be related in large part with these outflows from the LMC. And here, just the oxygen-6, typically in collisional ionization, will peak around 3 times 10 to 5 Kelvin, carbon-4 around 10 to 5. And you can see that over ions at higher redshift, we can use neon maximum 10, but not in the LMC, oxygen 6, 7, that's X-rays, and we cannot do that, or, well, I will not talk about it anyway. So I'm going to show several results. One of them is the survey, which is already now 13 years ago, that Chris led this fused oxygen 6 survey. And the survey was selected to use the best 12 early type stars. And here the best stars mean that, so here you have now the flux as a function of wavelength, and that's basically the region around the oxygen 6. And here you have this oxygen 6, so you have these two components, Milky Way, LMC. It's a doublet, so you have information about the 1037 line that is here, but it's a complete mess in the LMC. We can't use it, unfortunately. So what they've been looking is to have very smooth continua, and at least they tried. Some of them are not as smooth, they are more complicated. But at that time, they actually look at many more stars. There were already many more stars that were observed, but the sample ended up to about 12. And in each case, they detected oxygen 6 that was associated with the LMC. And as I'm going to argue in the next three slides, this work really provided the first solid evidence of large-scale distributed gas around the LMC. There was another paper by Walker a bit earlier using STIS and observing carbon-4 in quiescent region of the LMC, and where they already argue that there was a component that was not associated with directly the star-forming disk galaxy, forming disk in the disk of a galaxy, sorry. So one way to know, because we have this great view of the LMC, we can actually study the spatial variation in the column density as a function of a region that you're looking. So here, here is a circle, that's the size of a circle for an oxygen 6 column density of about 10 to 14. So you can see most of them, except maybe this one, are all larger than 10 to 14 oxygen 6 atoms per square centimeter. When you look at this, you can see that there is large variation in the oxygen 6 column density. You can maybe think that there are some enhancement toward some very active region, but you find also pretty strong or weaker oxygen 6 toward the same active region. So there is a large variation in the oxygen 6 column density of both small and large angular scales. Another survey that I want to show is a sample of 70 stars, and that was done by Patak. Sorry, don't know how to pronounce his name. But that was done about 4 years ago. Now they actually increase the sample. They look at more complicated spectra. And what they found here is it's basically the same conclusion with a much larger sample, the same conclusion than Chris et al. In 2002. There is strong oxygen 6. It doesn't seem to care about the region where you find it. There is large variation. And there is some enhancement, and that was already pointed out by Danforth and Bill in the room, using one superbubble. Here they have a few more, so this result is actually strengthened, where you have some enhancement, about 0.3 dec. And the thing that I will say regarding the SMC, they did a similar study, and they actually find very similar result, in particular this enhancement toward the very active region in the SMC. And of course, talk to Bill, because he has a survey in progress on this. But Patak et al., they only studied the oxygen 6, so they didn't have any information about the other gas phase. And that's very important, because one of the things we want to know is where is actually this oxygen 6. Does it go exactly where this neutral gas is, mostly in the disk of a galaxy? Or is there any evidence that this gas is extending well beyond the disk, or at least extended in velocity in space? And so here that's, again, normalized profile as a function of the velocity. Here you have the around 2 lines now, the LMC component on both sides. Then overplotted with a fixed solid line is the oxygen 6. And I don't have to go in much detail. You can look just at the spectra. It's pretty striking. The oxygen 6, again, doesn't look at all with like the around 2. It's much broader. But it's not just broader, it's also, it seems to be decoupled in velocity, meaning that most of the absorption is not, or lots of the absorption that you see in the 6 is not associated at all with what you're seeing in the iron 2. And so one way to do this, to see that, is do this plot again against the H alpha map of the LMC. And actually, most of the targets that we've been studying show that the gas is actually coming from the LMC, not going toward the LMC. So this gas is possibly outflowing. But is it really that? And that's the new project that Kat has been leading, and where we selected, not on purpose really, it's just because it's there, but the idea is we're going to look in the region of the LMC, this little square here. And that's Kat, beautiful slides. And what we have here is a disk star and a QSO. It's a background QSO behind the LMC. So now we have the information not only about the gas that is in front toward the stars, but also the gas that goes through the entire disk and halo of the LMC. And so what we're doing really is what we're doing at higher redshift, but it's a simultaneous experiment where we're doing both the down the barrel observation and the transverse observations. And so again, that's a region that we're looking, and if you zoom here, that's the star, and you can see a wind nebula that I'm going to actually see this in the spectrum. The systemic velocity, so the way that we determine this here is that we're using the H1, and we're saying that the average here, peaking here, is basically our systemic velocity of the H1 gas along these two sight lines. And these two sight lines are only separated by 100 parsec, and when you look at the H1, there is not large variation, so we just use one velocity for both sight lines. That's the, and now it's actually absorption, but this is now plotted as apparent column density profile. So we transform the normalized profile in this apparent column density profile as a function of velocity. And here we're just focusing around the LMC. And what we're seeing here, next just show again the span of the H1 emission. So we're missing some absorption here. That's because the H1 probed the entire gas along the disk. And we see all this absorption in front. And some of this absorption here, this is H alpha, thanks to Yuha Chu. She gave us this beautiful spectrum. And actually, we can see here both the expanding shell, the expanded shell of the Wolf-Rayet stars that we're studying here. So here you have the H alpha. Here we see it in absorption, silicon-4. We don't see the other side because, of course, we can only see gas in front of the star. Well, let's go back now to the QSO, so the target where we probe the gas all the way through the galactic disk. And here is the carbon-4 and silicon-4 overplotted, and you can see that it's very different from what you're observing toward the star. It's very broad, so you see absorption on both sides, and it extends well beyond what you're observing in the H1 disk. Well beyond. It goes the H1 disk here, stop around 250, I believe, and we go up to 100 kilometers per second here. So we have gas that's coming out, and we also gas that's coming out from the far side of the LMC. So that's basically the velocity that we're probing. It goes. So here it's put in the LMC frame along this line of sight, and we see gas that absorption in the carbon-4, sorry, and the silicon-4 that extend up to plus or minus 120 kilometers per second. Could it be something else? I'm running out of time, so I will just go very quickly on this. Talk to Kat if you need more information, but basically we have ruled out that it can be rotation for a thick disk. We have ruled out tidal debris. Basically, there is in this direction, there is no evidence that you could have some stream gas along the line of sight. So really, what we're seeing here is large-scale feedback-driven outflows. And when you put now these two pictures together, so the fact that when you look to a QSO sightline through the LMC, you not only see gas that is expanding away on the side, on our side, but also on the far side of the LMC, plus the fact that the oxygen 6, when we study the oxygen 6, it doesn't really care about what's happening in the galaxy. It's all point out to a very large extended halo gas that is certainly expanding from the LMC. And so, just to finish with some numbers on this, it's when here it's now plotted just toward the QSO. Here we show the oxygen 1 and silicon 2 of a protein, and we multiply this, and basically that tells us that the gas is very much ionized. It's 70% ionized for the warm phase, and the fact that we see a high ionic ratio of carbon-4 to silicon-4 tells us also that this gas is collisionally ionized. And not only that, but also just the breadth of the profile is clearly not consistent with this gas being photoionized. And actually, when you look and we actually compare, I don't know if I can show you offline that we have oxygen 6 absorption toward the star, and we overplotted with a carbon-4, and actually on the side where we see that is probably by the star, there is actually an excellent match between the oxygen 6 and carbon-4. So this gas, carbon-4 is silicon-4, are truly probing this also this highly ionized gas, hot gas. In terms of mass, so this is we run a simple model. It's a binocanical model where the gas just outflowing on both sides. And we derive the mass of the metals and the mass of the gas, and in terms of bionic mass, it's about 10 to 7 solar masses. That is pretty small in comparison to what you have in the Magellanic stream, for example. But it's actually the mass outflow rate is actually higher than the current star formation rate in the LMC. In the future, one of the goals, and that's an idea of a program that Chris has proposed a few years ago, is to actually, and where the data are there, it's actually to look beyond just the disk of the LMC. So we've been studying stars in various locations toward the LMC, and this CALEF, this QSO that goes through the disk of the LMC. But we have also in the database, the COS database, we have also QSO that are well beyond the disk of the LMC. And below, in red, below the name of this QSO, I put in red a quick look that I did last week, using in particular this paper by Andy on the Magellanic stream, where he listed, where he showed the spectra. And that's the different component that you see that are directly not associated with a Milky Way disk. And you can see that you have pretty high velocity component that could be also LMC gas, well beyond just the LMC disk. So it could, the gas on the LMC could extend well beyond the LMC disk itself. Now, of course, it's not all that easy because we know that there is a Magellanic stream, and so it will be tricky. It's going to take some time to actually try to separate clearly if all this is really LMC halo gas or if it's actually a Magellanic stream gas, for example. So we'll just put my summary. I hope I did convince you that the old and new observations of the LMC have shown that you have a highly ionized gas that is clearly not related directly to the star forming, the immediate vicinities of the stars. The gas is multi-phase. It's in oxygen 6, carbon-4, and silicon-4. It can be extremely broad. So that means you have several components, or you have turbulence is dominating the broadening of a profile. And all this, when you combine all these different points, is really point to that you have this large-scale highly ionized motion in the LMC. There is not, at this point, anything really convincing that what's happening, the present stellar activity in the LMC is really associated to what you're seeing well beyond the LMC disk, except for this slight enhancement in the oxygen 6 column density that you observe both in the LMC and SMC. So these super bubbles may enhance the oxygen 6 column density that you're seeing, but not, it's about a factor 2 compared to the overall, column density on the face of the LMC and SMC. And I will stop here.
Okay, we have a lot of time for questions, so fire away. Yes.
Any clues as to what causes this ionized gas or what's the production?
One of the mechanisms that has been argued is basically radiative cooling. That it's hot gas, but it's basically radiative cooling, and that actually can explain very well this type of oxygen 6 column density, because what I did mention is that this oxygen 6 column density, what we're finding both in the LMC and SMC, are at the same level or even higher than what you're observing in the Milky Way. Okay? So you will expect that you have a metallicity dependence, but actually when the gas is radiatively cooling, you don't have really dependence. So that's one way. You have other processes. You have many processes. It could be interface between the cooler gas, and we see that this gas you have cool gas. We don't know what's happening with the hot gas, but it could be that this highly ionized gas could be this interface between this cool gas and this hot gas too. The general problem with this type of model is that typically the column density are pretty small in these models, so you will have to add a lot of these interfaces along the line of sight to actually reach the type of column density that we observe. So that's are some of the models.
Sasha?
I have trouble especially with regard to the third point here, and the fact that you showed that there's very large, small angular scales variations. I have trouble to build a 3D picture of what's actually causing the angular separation variations. Is this depth along the lines? What's a fashionable way of understanding those?
Yes. So the question is, how do I explain this large spatial variation?
Yes. In terms of a large-scale outflow.
Yep. It's the only explanation that we have is that it's very patchy, which is not an explanation. We basically don't really know what really creates this. But one way to explain this is that the gas that we're seeing, this highly ionized gas, is actually very patchy. So there is this large variation in the column density. So you have regions where you have more highly ionized gas than others. But that's really not answering to your question. But again, if I want to picture a 3D, that's the problem with this studying near face on galaxies, is that the 3D information is actually very difficult to do because everything is projected. Yes.
You can compare this with the star formation activity in the background.
Yes.
So there's star formation history done by Harris and Tversky. You can compare it to the star formation rate in the last 6 million years and last 12 million years to see the supernova energy injection rate.
So I don't have an answer on this, but I will say that they try to correlate the oxygen 6 column density with the H alpha intensity in the background. I don't find any. They also try to correlate with the X-rays, but there is no question.
Stars.
So
star formation activity.
Okay, I don't think that has actually been done. I don't think that's a very good idea. Yes.
You mentioned 6 million years, right?
Yeah.
Because the star formation history they got is not good for such young planets.
So for Harris and Tversky, so they have 6 million year bin and the 12 million year bin. So 6 million years, that's for O stars to explode. 12 million years is for B stars to explode.
Yeah.
So there are two different epochs.
Yeah, that's a good
You have to
idea.
look at both.
Be done.
Bill, you had a
You
question.
can do it.
I just wanted to make a comment that the spatial variation of the O6 goes down to much smaller scales even than these kind of large-scale pictures you've got up here now. Within a given star-forming region, you can see large variations in the O6 from one star to another that are right next to each other. So in star-forming regions, it must be very, very close.
Yeah, so I guess that's another problem of doing what you're proposing, is that when you even look at very small scale, and that's what, if you look back, stages. If you look back here, you know, they have many more data points here, okay? And if you, there is huge variation on very small scale. So even when you're going to try to do this, I don't think you can do it. Trying to do the experiment that you just said. I think it's going to be very difficult.